Welcome, or hopefully welcome back, to another episode of the Reliability Matters podcast. In today's episode, we're exploring automated optical inspection, or AOI, and X-ray inspection technology within the electronic assembly industry. Joining us are two experts who bring a wealth of knowledge and experience to the table. Joel Scutchfield is the General Manager of SMT and Semicon Business Operations and Director of Sales at Koh Young, manufacturers of automated inspection and precise measurement systems with its headquarters in Seoul, Korea, and R&D centers around the world. Joel has been with Koh Young for just under 10 years. Also joining us is Jesper Lykke, the CEO at Viscom, a manufacturer of inspection technologies, in particular for automated optical inspection and X-ray inspection. With headquarters in Hanover, Germany, and offices worldwide, Jesper has been with Viscom for 14 years. Both Joel and Jesper are widely considered to be subject matter experts on inspection technology. In this episode, we'll delve into the principles and applications of AOI and X-ray inspection, discussing how these technologies are revolutionizing the electronic assembly industry. We'll explore the latest trends, challenges, best practices, and future directions, providing you with a comprehensive understanding of how these inspection methods are critical to maintaining high standards in electronics manufacturing. Whether you're an industry professional, a tech enthusiast, or just curious about the intricacies of electronic assembly, this episode promises to offer valuable insights and expert perspectives on the inspection technologies that are driving both innovation and quality in the field. So, sit back, relax, and join us for an enlightening conversation about inspection technology. And it all begins right now. Stick around, this is going to be good.
Welcome to Reliability Matters, a podcast for the electronic assembly industry. Each episode covers topics related to reliability, best practices, and environmentally responsible assembly techniques, with insights from experts across the electronic assembly industry. Now, here's your host, Mike Conrad.
Joel Scutchfield, Jesper Lykke, welcome to the program. I appreciate you guys being here today.
Thank you. Thank you for having us.
Yes, absolutely. Pleasure. Pleasure is ours, Mike.
Oh, well,
you're quite the known source in this space.
Oh, well,
quite the rock star.
Well, let's just change the episode to make it about me. Let's just do that, huh?
Good idea.
I don't know. We probably don't have enough time. Anyway, thanks, guys. I really appreciate your willingness. And one thing, we started talking before we went on air about this, but one thing I really appreciate about our industry, and I don't know if it's completely unique to our industry, but it's certainly unusual amongst industries in general, is even though many of us are all competitors, there's a tremendous amount of collaboration within our industry. And we see that at technical conferences and symposiums, and we all have the sales team out there trying to sell our wares and be unique and stand out. But in the technical world, there's an awful lot of collaboration and sharing of information and a joint mutual interest in educating. And I think that's what makes our industry perhaps a little bit unique
I think
compared
we're all
to some others.
trying to pull on the same end of the rope, right? Try to expand this industry for the betterment of everyone, right? And all of us that are involved. And now we're in this phase of trying to recruit the next generation to come in and take over for, those of us that will at some point find our way to the golf course
Yes.
on a more regular basis.
Golf course
And,
or a beach or just fill in the blank. Yeah, absolutely.
There
Come
you
on,
go.
young people, get going, right? We're waiting for you.
Challenging. It's a whole nother topic, but it's a real one, right, Mike?
But it makes its way into all these, every episode I have on whatever subject we're talking about specifically, the great retirement, the silver tsunami, all the grain out of our industry, however you want to put it. It comes up because younger engineers are leaving university and coming into our space, and we've determined that universities teach, if you have an EE degree or a BS in electrical engineering or whatever the case may be, you understand how electrons work. You don't necessarily understand optical lens, one optical lens over another, or
how to assemble a
squeegee
circuit.
or squeegee pressure, or the best way to apply a thermocouple for temperature profiling. That's just way too down a rabbit hole. That would be a 40-year degree, which we just call work experience. So there's a lot of tribal information in our space, and that's why we do the show, so that we can record some of that tribal information and maybe cover some of the points that one doesn't discover until they show up for the first day of work, and get the deer in the headlights look.
Give them a head start. That's good.
Yeah, exactly. Kind of this information vault, by mind melding all the great information industry experts like yourselves have and documenting it somewhere. So
Absolutely.
Let's start with a comparison. I'd like to start at the very basic level, kind of a 30,000-foot view level, for the sake of some of my audience that may not be quite as deep down the inspection rabbit hole as you are. So let's start with a basic comparison of the different types of optical tools for inspection, from microscopes to AOI equipment and everything in between, and then the different types of that AOI. Let's give us a kind of a 30,000-foot view on what various technologies what they're capable of, and at what point should someone consider upgrading from like a jeweler's loop or a simple microscope to something a little bit more sophisticated and with more capabilities. So I'll let whoever wants to start can start, and then we'll just kind of pile on from there.
I'll take I'll take you into the Wayback Machine real quick here.
Oh,
Mike,
you're Peabody. You're Peabody and Sherman. We grew up with the same cartoons.
That's right. You mentioned the basic manual inspection tools that were available back in the late 80s when you and I got into this industry, and that's exactly right. I mean, I remember using the Luxo ring lamps and then watching that transition, from my manufacturing days, where we didn't have automation in that particular time within this evolution of our industry, up through moving on to the sales side in the mid 90s and starting to see some of the tools that were coming into play, and very basic, migrating now from ring lamps and magnifying lenses to tabletop inspection systems, laser based for checking solder paste, shape, solder bricks, and some of the other offline tools, the 2D tools that were used initially, to then finally into the higher level means of automation, beginning in the 2D world, and then eventually into the 3D world. Actually, with our introduction of the 3D AOI system back in 2010, and then everything in between. I think from our perspective, and I'll let Jesper add on to this. We try to impress upon the fact that, look, there's a lot of things in the mix here, right? There's 2D still in existence. That's kind of where AOI came from an automation perspective early on. And even in the 3D world, there's different mechanisms. There's Moiré interferometry, there's laser based, et cetera, some combinations of both. But there's also a big differentiation in the use of the individual technologies that I'm talking about, and how we get the results that we are providing. So, I like to say, what's under the hood really matters, right? There's the right kind of information, in particular in the 3D world, which is, very parametric, objective, measurement based. Then it has to be gotten the right way, right? You have to, again, what's under the hood does matter, the accuracies of the subsystems, and then the right amount, right? In this particular day and age of data usage and data really being now the currency for smart factory realization and how it's utilized, you really need all three to be able to really take your business to the highest levels that you can from the standpoint of yield improvement, cost reduction, reduction of the human element, which is, again, back to the comment we made earlier on. So it does run the spectrum. And I think at this particular juncture, most companies out there, unless you're really, really small, have some level of automation, whether it's offline or inline. And then it's just a process of how you take that forward, how you decide to take that forward based on your needs or what you're trying to achieve, and then utilizing the various systems and technologies that are available.
Well before any of your companies were even in existence, I used to use 3D inspection technology way before anything even plugged into the wall. You just had a giant magnifying glass, and you took the subject and you just rotated it underneath it.
Yes.
Yeah,
3D,
that was
right?
it. That was it.
Our eyes sees things in 3D, so that was the most basic. Now, it took you guys a lot of years to figure out how to have a computer do that, but it was easy back in the day. Jesper, what's your take on the 30,000-foot view of the various technologies that are out there and their capabilities?
No, as Joel said, so a microscope is actually absolutely good for some things. It has to do with your volume, short description. So if you produce one board, which I don't think many people do these days, but as Joel said, there's some automation portion of it. So as soon as you have more than 10 or 20 boards, you would need some sort of automation, maybe not fully automated, semi-automated, AOI, X-ray, manual X-ray, whatever. So there's always the need that needs to be, let's say, decided first. Obviously, going out there and buy some equipment is costly, but of course depends on your volume. There's a cost reduction in other ways where you get the return rather quickly sometimes because you have it automated. And you are more consistent. Machines catch defects more. No offense to any operators, but even myself, after looking at the same board for more than 2 minutes, I can't tell up and down anymore. And that's really what it is. Obviously, there are more skilled people than me that does that, luckily. I'm not a manual human interface optical inspector. But automation is absolutely key for getting a consistency out the door, so the customer of our customers are the ones benefiting, definitely.
Yeah, I think that's the key, Jesper. That quality is the real driver here at the end of the day, and people were able to get away with those less sophisticated systems for many years because of the complexities at the time and so on and so forth. But ultimately, the cost, quality, all contribute to the need, and really is what's driven the automation and the advancement thereof.
Yep, agreed.
I love the way you guys answer questions, because there's like 4 questions that I had for you next, and you've already answered them. This is great. This is awesome. I can just sit here and ask one question, and the whole show writes itself. This is great.
You'll have an editless episode, Mike. How about that?
Exactly. Yeah, that'll be a first. Let's Jesper, you mentioned about I think you may have used the word consistency or something to that effect, how automation systems provide this level of, kind of higher level of consistency. So let's dive into that a little bit. The original inspection system was these 2 things. I'm pointing to my eyes for those listeners. We just looked at boards, and then as boards and components got miniaturized, now you can't even see them. So even with my little, cheater glasses, I still can't see half the components on a board. So we started using magnifying glasses and loupes and things like that. And then companies like yours come along and they said, "Oh no, we can show you on a video screen, on a larger monitor, and you can zoom in and out and do things like that." But originally, it was still an operator looking at the image. You guys brought the image to the person's eyes so they could interpret it. But ultimately, it was still an operator looking at an image. And, I'm reminded of like MRI images and CAT scans and things like that in the medical world, where even a physician that ordered the scans is probably not going to read them. They're going to have a radiologist or whatever the position is called, because they're experts at seeing patterns and randomness. And to me, it all looks like the old, over-the-air televisions that we grew up with. When the station went off the air, it was just snow, as we called it. But they're seeing stuff out of that. Now, that's probably an extreme example, but the point I'm making is at some point, your job is to deliver more than just a clear image to the person who's seeing it. At some point, there needs to be able to provide a little bit more consistency and accuracy. There's got to be some computer-aided interpretation going on. So at what point did automation systems, or inspection systems, I should say, go from just a nice, clear, big image to interpretation of that nice, clear, big image? Is that a clear question?
Yeah, absolutely. So if I can start that one, so yeah, I mean there are a couple of things embedded in those questions. So one is to answer your last question first. I don't know. We have used AI, quote unquote, or a version thereof for many years. Had I need to guess, I would say maybe 8-10 years ago or something like that, where some sort of AI started, where you needed some feedback from what you already had done in the past to make sure that what you have now is still being caught as defects or passes or whatever. So there's definitely an aspect of it there as well, that you need to have this, as I said earlier, you're right, consistency. So one is that the machine is not only taking pictures, obviously, that there's a lot more to it than that. I'm sure Joel would agree to that. So it has to do with resolution, of course. It has to do with the software, of course, as well, how you interpreted it. So the machine can do a lot for you, by all means, and it always has been able to do that, and we'll get to the future a little bit later in the podcast. But to go back 8-10 years, I mean, as you said, Mike, the machine would take pictures, and it would interpret those in a certain way, but you would absolutely need that operator input, really reading out the images and whatever the machine called out. This is a defect, this is a missing component or a missing solder joint or anything like that. There was a lot more tuning back then to get to that level. And these days, obviously, I mentioned it already, AI is a huge help for everybody, ourselves included as a manufacturer of machines. But definitely the key is that the customer and the end customer obviously get a huge benefit from it as well, that the quality of these products that leave the production floor is by far way better than it was, let's say, 10 years ago. And for the most part, I would also claim it's still a lot of effort, don't get me wrong, and I know there's a lot more than what we're just mentioning here, but it definitely helps all parties to get better at what they do. That's the bottom line for sure.
Excellent. Joel?
And to add on to just one of the comments that Jesper made, he's right. I mean, we go back 10 years, even more, into the original 2D systems that were introduced. And that was really the first, Mike, as you said, first run at utilizing technology to make a decision, right? To tell the operator, okay, this is what I'm seeing. You have a choice. You can verify that I'm seeing it correctly, or you can dispute it, right? And in that case, you're going to tune, you're going to do other things. But in that 2D world, there was a lot of variability, and that still exists today because some technology, some approaches being used still use a larger element of the 2D aspects than we would like to see, okay, for reliability in analysis. And what I mean by that is, in the 2D world, you're basically getting a top-down view, right? The old bomb sight approach, and you're subject to warpage, you're subject to thickness differences, you're subject to a lot of variability, and that played into really needing the operator even more so to make those assisted determinations. I think things changed significantly with the introduction of the 3D measurement-based systems. Now we're taking all that variability out. Ideally, we're not using those 2D methodologies to do things like body and lead tip find, because that's what you use. That body lead tip find sets all the other regions of interest in terms of what you're going to inspect for, solder, OCR, OCB, et cetera, et cetera. So if you don't get that right, you're in a world of hurt. That's where your false calls come from. So that's the major advantage of the three-dimensional aspect, is that we're using measurement-based information. We're using, again, parametric, objective, concrete. It's not binary ones and zeros. It's very specific. And now from that, everything becomes much more repeatable and less dependent on the human aspect, as your question alluded to initially, Mike. So hope that helps just throw a little bit more into how all that comes together.
Absolutely. There's two things that we inspect for, or there's two end goals for inspection, is from my layman point of view as an inspection expert. One is to prevent escapes, things leaving the factory that would not be desired. But even more importantly, to prevent rework, to prevent the mistake from happening in general.
Fix the process. There you go.
Fix the process rather than repair the board. Because, of course, we all know every time we rework something, it adds another layer of, potential liability or risk. So,
and a lot more cost.
And a lot more cost. It takes usually longer to rework something than it did to build it in the first place. So tell me how inspection systems can maybe kind of not just prevent the ultimate escape, the great escape, but can actually fix the process or identify things in the process that have to be fixed so that there is no rework necessary. Maybe that question kind of goes down the SPI, AOI rabbit hole. I'm not sure, but I'm not going to attempt to answer my own question, but tell me how one can use this type of technology to prevent the problem in the first place before rework is necessary.
Yep.
Jesper, you want to start? Go ahead.
I'll start, and then I'll let you talk afterwards. We already alluded to it a little bit as well, of course. So it has to do with, let's say, the process itself. So an optical inspection system, an X-ray system is a process tool. So you can use it in many different ways. One of the ways would be, obviously, you fix your process. So it would unbiased tell you your process and how you operate your other machines for that process. And it will not let you down in many ways. That means it will absolutely find your defects, and it will definitely tell you if you have a problem with the process somewhere. And that's definitely also the good news, because you can improve a lot when you get the right equipment in, and it will tell you even before you're done with the product at the end of the line. So that's why you already mentioned it, Mike. There's SPIs, there's post and pre-reflow AOIs. So you can decide in your process where you want those test gates and process improvement tools, so you ensure that your manufacturing floor is producing real non-defective boards, and that you don't even have to process it afterwards, as in rework it and things of that nature.
Yeah, and a good example would be what the SPI tool, solder paste inspection tool, can do for you in the manufacturing process. And we always recommend, when we walk into a customer that has no inspection technology at all, aren't too many of them out there today, but we always recommend starting with SPI. I think it's pretty widely known throughout the industry that somewhere in the neighborhood of 70%, maybe more, of the solder-related defects that we incur come from the print process. Not necessarily the printer itself, but the print process and everything that goes along with it.
And just for the sake of my audience that may not be quite as familiar with all these acronyms, SPI, solder paste inspection, as opposed to general inspection. This is a very specific inspection.
Correct. Yeah. As soon as the paste has been deposited on the bare board itself, we want to check it right then and there, right out of the machine. We're going to look for position, XY. We're going to look for thickness. We're going to look for shape. We're going to look for all kinds of anomalies, hotspots, trends that might indicate that maybe that print process is not in control to the degree that it needs to ensure that we're not building in solder-related defects. And again, why not eliminate that 70% of potential defects right out of the gate rather than start with an AOI machine, optical inspection further down the line, where we're just verifying that, hey, the print process is out of control. And too late. Now we're back into the rework. So, we start with the SPI, and as Jesper said, there's multiple points at a pre-reflow. In a pre-reflow environment, now we can verify that it's the right part, it's in the right location, it's the right polarity, it's all of those things before the solder joint is formed, which again reduces cost if there is a problem. We also now use that data to make adjustments to the placement system if needed. Maybe we've got a problem with a feeder, a spindle, a nozzle. We can tie the information specifically back to those contributing factors, and then finally in the base assembly process post reflow. Now we're looking at the solder joints themselves, right? Are they acceptable? Are they meeting IPC standards for whatever class you're building to? Did something happen in the oven? Did parts fly off? Is there now? Do I have an oven issue? Right. So when we talk about process control, as Jesper alluded to, that's how we're doing it. Right. We use those multi-point islands of inspection, basically sensors, to provide us with data that tells us either things are great or we need to make some adjustments. And as we go forward, now that's becoming much more automated with AI and automatic feedback and self-healing, all those kinds of things, to the point where the operator doesn't have to be as involved in doing any of that. So that's exciting. That's our future. That's our Industry 4.0 smart factory realization initiative that we're all working toward, and quickly on a track to achieve. Already are in many cases.
Well, I think everything you're describing is certainly the building blocks to the so-called lights out factory. I'm not a big fan of that term because I take these words very literally. I'm like, no, I mean, someone's got to sweep stuff off the floor. I mean, it can't be completely lights out. That would be a little scary. But the general context of not relying on operators to make split-second decisions, red, green, go, no go, pass, fail kind of decisions, and learning. One of the advantages that AI has is, first of all, I do not like, and I've railed on this before, on this and other shows. I'm not a fan of the term artificial intelligence because there's nothing artificial about it. We learn by reading. We go to school, they teach us things, we have to read things. It's acquired intelligence. And I think one of the reasons there's so much fear, and there's a basis for the fear, obviously, but one of the reasons the fear is even more exaggerated is because of the word artificial. When we go to school, we're not artificially taught. We acquire knowledge. AI acquires knowledge the same way. It just reads a whole lot faster. It's read over 1 billion books, and it's generative, so it forms opinions. So are we. It's not human, but it's learning from humans. We taught it everything it knows, and it doesn't know anything that we have not taught it yet, or it has not learned from us. So acquired intelligence. But AI, certainly in your world, just makes a whole lot of sense because operators, humans, cannot make decisions on the fly fast enough. And we don't have, eventually if we do something long enough, muscle memory sets in, but we don't have, infinite memory. And computers, algorithms, and it has infinite memory, and it can actually start weighing risks like an underwriter would, and all that. And I would imagine, going a little off topic here, but I would imagine that beyond, or going back, maybe the original motivation for automated inspection is to make sure that the right component is in the right place, the polarity is correct, it's not skewed, it's not standing straight up, whatever, some obvious soldering defects. And I would imagine that with the technology that's just evolved rapidly in your world, that things like maybe counterfeit detection and other, maybe less obvious applications can come out of that, right? Because if you're inspecting a component to make sure its polarity is correct, you're seeing a lot of things beyond the polarity, and you're capturing data well beyond positive and negative, right? So what are some of the other maybe less obvious? I said counterfeit detection is throwing one example out, but what are some of the other additional benefits beyond what the stereotypical basic view of the benefits of inspection provide? Throw some examples out beyond counterfeit.
You want to start with that, Joel? Then I'll jump in afterwards.
Yeah, I'll touch on it and I'll let you close it out. Interesting. IBM Watson has been running an ad. I don't know if it was Forbes magazine or where I saw it recently, but something to the effect. It's very simple. It said something to the effect that if you're going to rely on AI to make a decision for you, you first must need to understand what it's doing, right? And how it's doing what it's doing. And I think that's really the key. And Mike, you alluded to the fact that, we are teaching it, right? And so when we, as manufacturers of solutions-based systems, sit down to better understand how we're going to utilize AI, we first have to answer those questions, right? First of all, what is our objective? What are we trying to do here? Okay. And then we start with making sure that we have the expertise in place to train those algorithms properly so the generative piece can take over. So it takes time. It's there's a lot of stopping and starting, right? There's a lot of data acquisition, data analysis. Well, what are the results? Go back, acquire more data, analyze more data, analyze the results. Continue, and while this is going on, we're continuing to refine and develop the algorithms themselves. So, there's many areas where this can be applied. Obviously, in the programming effort to automate programming more completely. Again, removing human dependence aspect, creating situations where now we can allow the system to learn what various defects look like, so it's better apt to catch or highlight something that is an anomaly. And then certainly when we're talking about closed looping processes, where in our case we have what we call our KPO tools, our Koh Young process optimizer for both the print process and the pick and place process, where we can literally take full control of the screen printer for things like squeegee speed, pressure, and snap off of the stencil, and doing that by using machine learning and ongoing analysis of trends and automatically making adjustments for those things. So it's completely hands off. A similar in the pick and place environment, where again we're detecting pre-reflow what those various anomalies are and able to automatically adjust. So again, you have to really you have to have the data, right? You have to have the right kind of data set. You have to be able to construct your proprietary AI engine, building it around that that data set that you know very well, and then applying it using, your process expertise to adjust and tune those algorithms as you go. And that's really the base application for how it's being used. And again, the application, I touched on a few of them. I don't want to steal any Jesper's thunder here, so I'll let him talk a little bit about their aspects as well. But that's just the base approach, and it certainly is, as we've all noted, something that we'll continue to use and develop and expand as we go forward.
Excellent. Jesper?
Yeah, no, I would agree, of course. I mean, the approach for all of us is, let's say, somewhat the same. We want more data, and the data will get processed. So, I mean, 40 years ago when we started, I mean, the AOI machine back then, computer power and let's say hardware and the human interface back then was obviously vastly different than what it is today. So the driver there was let's say throughout those 40 years has been let's say data. And lately, obviously, with the AI, you get a lot more data, but it's also the same thing as you, both Joel and Mike, you guys said. They say garbage in, garbage out. So you need to make sure that you feed in the right stuff, chat GPT and whatnot these days. I mean, you get something out, but you don't really know where it comes from. And that's exactly what Joel was saying as well, that you want to keep that closed process, closed loop interface, we call it, but yeah, the same thing that you have the SPI speaking to the AOI and then further down to the AXI or MXI to narrow down, okay, you don't need to waste time on inspecting in details this board and this location, but it already knows that from the SPI or AOI, well, I know I have some abnormalities there, so you want to focus and maybe strengthen the inspection in certain areas of the board where one of the SPI or AOI machine or whatever found some potential defects, and then you can drill down and have the machine automatically select that and say, well, I found this chip resist or whatever, it didn't look right. It may not quite look like a defect, but definitely look a little bit closer. And that's when further machines down the line can then look closer, laser focused on those exact areas and components that was called out earlier, and therefore also eliminate false calls that obviously nobody wants. So it kind of double checks or takes an extra look at certain components that was found by the machine further down the line. So obviously you want those stop gates, as Joel talked about earlier. You want to stop after the SPI and make sure that everything is okay. You want to stop before you feed it into the oven. And yes, you want to stop after the oven, make sure that the 3D profile of the solder joint looks right, and even components on the shields and things like that. You want to make sure that the shield is located correctly. And of course, then you need the X-ray to look under those shields and make sure that everything will solder correctly. So it all comes together, of course, and it's all data-driven. It's a matter of where you can grab the data, if that's an SPI, an AOI, or X-ray for that matter. It all, at the end, feeds up to whatever NES software that's used. As any other company, we all have our own. But of course, a lot of our customers have their own as well. So we just need to feed into that system, and the more data you can feed in, the better result you get out.
Excellent. And you said the word X-ray, which is perfect segue. One of the to me, I mean, X-ray's been around for over 100 years, and it's amazing to me to think that back then, you know, we had the ability technically to see through things, right? That was amazing.
Easy.
I remember the early days of BGAs before X-ray was used, you know, in our industry the way it is now. The way to inspect under a BGA was with this oblique angle viewer. It was basically a microscope with a little prism, and it just looked underneath the BGA. Of course, back then,
first
BGAs
row, all the way around the
first
outside,
row.
Right?
You knew that the first row was at least the edge facing side of the first row was soldered properly, right? You had no idea about the hundreds of other, you know, solder balls underneath, you know, what they're like. I guess you could make a statistical analysis or an assumption based on it, but that was how, you know, that was the only way to do it. And then some clever person, maybe it was you, Jesper, I don't know, but some clever person in our industry said, wait a minute, we use X-rays for so many things, let's use it for this. And X-rays born into our industry. Can you explain, Jesper, I'm going to focus us on you because you guys do make X-ray equipment. And maybe by the end of the episode, Koh Young will start making X-ray equipment too. But they're probably working on it right this second.
Welcome.
Right, welcome to the world, right? But explain what role X-ray inspection plays in the inspection world and what differentiates it from other types of technologies.
Yeah, so I already alluded to it a little bit. So optical inspection, SPI, AOI, it's all visual. What you can see, the machine can see. Obviously, it can see it a lot better, higher resolution cameras, all that. The 3D aspect, of course, as well, where we have different ways of measure the volume. But for X-ray, there are the things that you cannot see with the naked eye. So let's say a polarity mark, of course, anybody can see that it's either like a laser marking or some sort of mark on the board or on the component itself. But X-ray you can look through, and by the way, the BGAs 20 years ago, they were huge compared to what we see today. Obviously, BGA balls and whatever, they have shrunk significantly. So here as well, you need the high resolution, best case inline or manual inspection as well. So there are, let's say, two different categories. One is more the lab style manual inspection, where you can do either lab analysis, or you can do some sampling testing, or you can go all in and then do a full inline X-ray inspection where every single board is inspected. Or even if you want to combine the two a little bit with what we talked about earlier, optical, then you can even combine that in best case one machine to save floor space, and you can have optical and X-ray in the same machine and working as a team perfectly together. But again, X-ray is something you need if you have shields over your components after the reflow oven. There may be multiple further steps before it goes to the X-ray. But there are things you cannot see. You already, Mike, mentioned earlier some components that may be counterfeit, and those are the things that you with extra high resolution inline systems you can catch right then and there. They would be looking differently, maybe not with the naked eye again, but with the X-ray you can see there are some wire bond wires that looks differently from a counterfeit component to a real component, and that can absolutely be caught with X-ray. Component placement and missing and all that, of course, on the shields is obvious. BGAs, like I already said, I mean, they are shrinking by the minute as well. Of course, everything. If you look at the newest phone, they were talking about a nano height of whatever new package type they have on there, and it saves still 2 nanometers or whatever, something, right? So it's just shrinking by the minute, and for that you definitely need to be upfront and on the forefront as well with the technology and make sure that you have the high resolution images to again feed to the AI and the operator obviously also at the end. So yeah, AI goes in here as well. Of course, it's the more X-ray images you feed in, the better output it will get, and the less the actual operator is needed, only if there's some extra critical components where the AI would say, well, it's better to have a human interface here and make sure that that's what I'm calling out. And that's also where we add that it's not only it bypasses the operator sometimes if there's some, call it simple defects, I mean a missing component, yes, okay, you don't need an operator to verify, yes, it is missing. But there could be some other instances where it's more like, well, it's shifted by 24 degrees and the criteria says 25. Well, okay, maybe it's okay that it's only 24 degrees shifted, right? So it depends on the criteria, of course, and where this electronics is going. If it's something that's going in a space rocket, that's a different story. That's a little bit more high end, of course. Versus if it's going into a DVD player, which almost doesn't exist anymore. But it really depends, of course, on the application. But the bottom line is, and the goal, of course, is that you attack all areas where you could potentially see some defects and that goes from SPI, AOI, and X-ray, or the combination of those two, AOI, AXI, to make sure that the product that you produce is in fact clear of errors and defects when it gets to the customer.
You talked about an example of a DVD player. That's what happens when we get, older guys, experienced guys giving examples, right? You're going to pull the DVD player. I would have said the 8-track player. So, we all have our
I
our line
under
in the
my
sand.
seat, Mike. Under
Yeah.
Driver's seat. Yeah.
I had one in my car, and one day I had in the 70s. I had an 8-track player that I added hanging below the dash.
There you go.
So, Jesper, every time I go to the dentist and get X-rays, they cover me with a lead blanket, and then they leave the room when they press the button.
Gives you a good feeling, right?
Yeah, right, exactly. And now, of course, I'm not in a containment vessel like the machines you build would provide. So I understand why that's necessary. But it did bring up the question. A lot of times, like if you're flying on a plane, they'll say that each flight, if you fly 12 times a year or 20 times a year, it's equivalent to one dental X-ray. So everything's kind of always benchmarked to one dental X-ray. But clearly, repeated exposure over time could be problematic to a person. I'm wondering, does the X-ray technology, the bombardment of X-rays onto a physical, non-human, non-organic thing like a BGA or a board, does that have any measurable degradation? Is there a limit to how many times a board can be exposed to X-rays, or the intensity of the X-ray, for lack of a better word, the wattage, the power, the amplitude, however it's measured? Are there limits? Is that a concern? Is it not a concern? Is it the equivalent to one dental X-ray? How do people who may be concerned about that get that answered?
Yeah, I want to be clear. I mean, you can't see my arms, but I mean, I don't carry around the lead vest all the day here, so we are safe. Luckily, there are regulations for that. Each state actually handle those things a little bit differently. But for instance, when we install an X-ray, the state afterwards will have to go in and verify that we do it ourselves, of course, upon leaving. So once it's installed, we do it like what we call an X-ray survey. So we verify that everything is within spec, and again, it's different from state and country and whatnot. And then you verify that, well, there's no extra leakage of this machine, and then the state will have to come in afterwards as well and do this survey. And let's say standardly, we would recommend to do that at least once a year. And there are, let's say, small personal dose meters that you can walk around with. Again, depends on the state and the company. Some companies require each person to carry one, and that we have one here in the office close to our X-ray machines, just as a safety precaution. If there's some sort of leakage, it would beep and go off, and you would know, well, now there's more exposure than what you would want, obviously. But yes, to answer your question as well, that there are definitely components that's more susceptible for X-ray exposure than others. It's always a good thing to know what each component was exposed to, and there are actually software tools that can calculate that as well. For a regular program, it can tell you this component was exposed by such and such amount of rad, and I think not all, but more and more components, especially the sensitive ones, BGAs and things like that, camera chips and such, they by now do get more and more spec. Sometimes, and I would claim that maybe not always, they know what they need to spec out as the component manufacturer. So they put it on the safe side, and it's like, well, you can X-ray it. Well, that's not going to work. So let's do the second best kind of thing. So it's obviously a balance. But it is very critical sometimes. I mean, a chip and a resistor, which are, I would say, considered old components these days.
Sure.
You can X-ray them all day long and nothing will happen kind of thing. Whereas some very sensitive camera chips or BGAs, yes, of course, or let's say memory chips or things like that. There have been examples of erasing memory if you just stick it in there for hours and hours, which again nobody does, of course. But we have done multiple studies with our customers where they were concerned about the X-ray exposure and say, well, can we do something, collaborate here a little bit, and we stuck it in there for half an hour or 2 hours and whatnot, and then they verified if the components was working and not afterwards. So there's the fear is real, I would call it, but not to the extent where you don't want to X-ray anything, because again, you need to look under those or through those BGAs, and with the 3D you can then verify that the ball is there, and
sure,
the, let's say, hidden pillow is another thing, and such.
Yeah, I guess it's all, at the end of the day, it's a risk-benefit analysis. Yes, technically there's a risk. What's the risk of not inspecting it properly? That's probably a much greater risk. It's like, I have a friend of mine that will never wear a seatbelt because they had a relative that died because the seatbelt locked up and they were trapped in their car and the car was on fire. And I mean, it happens. It's probably 1 in a billion versus, the odds of never wearing a seatbelt, right? So it's I get, there's, what was the old saying? There's 3 types of what was it? 3 types of lies: lies, damn lies, and statistics. So we see what we want to see in that. Before we leave the X-ray world and then wrap up our general conversation, time just flies during this show. Tell me about, we talked earlier about having the computer interpret what the operator has seen, so it's not just up to the operator. And I think in the X-ray world, and maybe in the other worlds too, computed tomography, CT, is incorporated into that. Because X-ray is, if you think about it, X-ray itself is a pretty dull image. I mean, it's a black and white image or grayscale image. It's not brilliant color. To a human eye, it might be hard to get some of the nuances of it, but when you add CT to that, all of a sudden it kind of rebuilds it in almost like an animated version of what we see with our eyes, and it can see things and interpret things that we can't. So how does CT work itself into X-ray? Is that part of every X-ray machine? Is that a separate feature? What are the benefits beyond just having a clearer image that it provides the user?
Yep. Yeah, so it really is for the most part of as a feature for every machine. It's optional feature, and you can actually overlay some colors to make it more, let's say, pretty for the human eye. But still, my 24 years with Viscom, there are some of those things that we do CT on is mind blowing when you see them on a picture afterwards, because you look through this mass and then you have all the inside details of here's the coil or here's this and that. It's just mind blowing. It really is, and there's so many, let's say, things you can do. So normally the CT takes it a little bit longer because it needs multiple more images. So it's not necessarily something you want to do for call it inline production. You can do some sample inspection. You can do it either offline or inline as well, where you can do some sort of a planar CT. It's let's say a little bit more limited, but faster version, where you can then inspect certain boards and make sure that you get the features highlighted that you want. And especially these days, BGAs have hidden pillow. That's always has been for the last, I would say, 10 years, a talking topic. Well, do you have hidden pillows on your BGAs? And X-ray CT specifically is a very, very good tool for that. And once you have that picture of the BGA component, you can then slice and dice it any way you want, and you can analyze it really. And that's what the CT is all about. It really is more long-term a lab tool where you can dig deep into the rabbit hole and verify these BGA balls, and you can verify your oven profile and solder paste amount and all that in the same scope. And you can really slice and dice as much as you want and have time for and verify that everything is working. That could be before and after a temperature test as well, a stress test of some sort, where you have, let's say, micro cracks on the BGAs and things like that. So there's a lot of good use for that. But again, it takes a little bit extra time. So it's not something you would want to do on every single board. But for that, you will either have the offline X-ray station, or let's say you would, in certain instances, verify every 100th board, where you would inspect it a little bit further and verify that you still have the same quality out the production floor.
I do love two of my favorite terms for solder defects. Coming from an industry that is highly technical, highly engineering centric, is head and pillow and tombstoning. It's like
Yeah.
You don't need to be an engineer to visually get a
right.
to
Figure
have a
that
concept
out pretty
of
quick,
what
right?
what
Yes.
defect they're talking about. Okay, last couple of questions. We have to wrap up. Like I said earlier, Koh Young is almost done engineering their X-ray machine, which they started at the beginning of this program. And
That's how long we talk.
I know, right? So what advice?
Just
and
fast.
Right, that was just like that, right? Joel's like, we got to do this because next time Jesper can't get all the talk about one type of machine.
It's all okay, man. All good.
Yeah. Let's start with Joel on this one. What advice would you give to assemblers, electronic manufacturers that are looking to invest in inspection equipment today? What types of questions should they be asking you, and what types of questions should you be asking them? What's the best advice?
Well, I think there's a couple of pieces to that, right? First and foremost, it kind of comes back to the discussion we had a bit earlier, which is there's various options here, right? So make sure you understand that each provider is in almost certain terms providing something just a little bit different in terms of 2D, 3D, how much 2D, how much 3D. It's kind of like the orange juice analogy, Mike. So you go to the supermarket and you pick up the orange juice container and it says 50% real orange juice or 20% real orange juice, and the rest is fillers and additives and all this other stuff, right? Very hard to find that 100%, Florida squeezed orange juice or whatever that commercial was, back in the 70s.
Back in the day, right? Back
What
when we were
was their
listening
name?
to
Yeah,
8-track
you remember.
players.
That's right, exactly. So, there's differences in technology still being offered. So you have to understand that. You have to understand that not all 3D is created equal. Again, there's some using a much greater degree than others to get that measurement based information, and that's critical because that drives towards the data set. The data set allows for all these things that we've been talking about for the last hour in terms of the use of artificial intelligence, basically the realization of a smart factory and the lights out, et cetera, et cetera. It all comes from that data set. So it's really important that you look under the hood, you understand how that company is providing the results that they're providing, similar to the AI question. The other thing that I really try to emphasize is that there's no such thing as a single machine purchase anymore. And you really have to look at this as a holistic approach. You're really looking to partner with a company that can take you where you need to be, and you need to understand their roadmap. You need to understand what kind of things they're working on, how much of their revenue did they put back into R&D, et cetera, et cetera. What's coming next. We didn't talk a lot about the data analysis software side of things, but tying it all together, tying into the ERP, the MES system, basically completing the closed loop, if you will, on making sure that everything is in fact tied together for this all-encompassing smart factory initiative. So, again, if you make the wrong decision on day one, you may preclude the opportunity to take advantage of everything else that you could otherwise have if you make that selection incorrectly. And I think the last piece, and Jesper will get a kick out of this, don't do paper analysis, right? And make a decision, right? You need to go out and see the equipment. You need to test it, take your boards. It's funny. I mean, now more than ever, it feels like that because so much of the research is done, online before they even decide to talk to us. There's a lot of preconceived notions and comparisons that are not always correct. Let's just put it that way. So, do your homework, roll up your sleeves and ask the right questions. As far as from our perspective, again, that runs the gambit as well, right? I mean, typically it's just sitting and listening. What are your issues and what are your aspirations as a company in terms of, your valuation of smart factory? There's various levels and not everybody needs everything, right? So, and there's also various flavors of technology, even within both of our offerings that might be better suited at a better price point for that customer's needs. So there's a lot of listening on the front end and, understanding of what their current needs are today, but also where they're planning to go as we go forward.
Excellent. Jesper?
Yeah, so I would concur with what Joel said, and one of our main tasks is to listen to what the customer is saying, not only, let's say, machine purchase-wise, but also future-wise. Okay, this is where we are going in the future, and then you collaborate and figure out the next best steps. But to go back to the machine purchase, I mean, it is crucial that the customers, our customers, they bring our boards and they go out there and visit us, because, again, support structure is a huge, well, it's not a sell a machine and run and I'll never see you again. Joel said that already. I mean, it is, you want to build up that relationship and visiting the different offices and seeing their support structure is crucial. It could be a one-man show selling one machine and we'll see. Obviously,
out of a garage, right?
That's not the case, obviously. But
there was a time, right?
We've all graduated from the garage.
That's right.
Don't underestimate.
So you
want
to get out there and you want to see it and you want to listen to the customer and we have obviously the best knowledge of our own machines and there is no one machine fits all customers. There's always some sort of customization. This is what you need. This is the price point. This is, let's say, where I see I will go in the future kind of thing. And then it's our job as a manufacturer to find the best machine for this need and say, okay, this is where you are today. But that machine that you're buying here is future safe. So it's already have the latest technology. It can build into the AXI machine if you would want to add that on later. It can build into the ASPI machine if you start with the AOI and things like that. So it's building the base and then obviously support the customers and listen to their needs. That's really the key factor here.
Very sage advice. And my last question is, and we'll try and limit our answers to less than a half hour each, or we'll have to go into a second part of this. Get out your crystal ball. Where do you see the future of inspection technology going? Maybe based on its trajectory, either from a hardware standpoint or a software standpoint or some standpoint I'm not thinking of. Jesper, why don't you start and then we'll end with Joel.
Sure. Yes, I mean, it is both obviously hardware and software, but I think I know for sure that the software aspect will take leaps ahead of the hardware. I mean, hardware is I wouldn't call it limited, but you can come out. I mean, some of the phone manufacturers, they come out with a new phone every year. That doesn't mean, and you look at that, if you see their release notes and whatever, yeah, well, this one has a tiny bit better chip and whatever. So it's really not groundbreaking technology all the time, and it can be, but hardware, of course, is a huge factor. You want to have the right quality hardware with the machine. You want to have the right resolution and the right 3D technology, as Joel also said. But I think here the future in the next 5-10 years, software is absolutely 100% where we would see the most benefit with the help from AI, of course, as we already talked about. that would take steps in the next 5-10 years. I'm 100% sure about it. And the hardware would seem, I wouldn't say sitting still, but it won't progress as much as the software. The software will, even though we are way far these days with AI integration and stuff, but you can only imagine what will happen in 5-10 years. That I think where the machines will be way more, let's say, software driven in the way that this is where we would see the advancements.
Excellent.
Yeah,
Joel?
I would agree with that. Yeah, I think, software is certainly at the forefront at this point. The use of the data, more and more AI, as Jesper referred to, as the chips become more enhanced and the capabilities continue to grow, using all of that to continue to reduce the human element, the need for human interaction, et cetera. And the connectivity piece, right, where we're feeding information back and forth, not to only ourselves, but to every system up and down the line, right? And the CFX initiative is playing a role in that. On the hardware side, I agree. It's going to be a little bit more static, but I do certainly see a lot more interest now on the back end, even things like box build and vertical assembly, where maybe we change the form factor a little bit, the handling system, to be able to do some things on the back end that are very different than the front end, which we've been talking about today. Even as far as adapting the actual inspection probe to maybe cantilever over a conveyor or be installed in another piece of automation that we don't even build, things like that. So that could certainly play a part as well. And then, of course, again, the software that ties it all together. So long way to go for sure. And, every
that's
time we
thing.
talk, that's why we're here, right?
Exciting. Live and learn.
Well, it sounds like none of us are going to have to turn the light off after we shut the door. It sounds like we all have job security, and certainly the need for inspection as boards get more complex and densities increase and component size decreases, the need for optical inspection and X-ray and other technologies that evolve from all that, it has never been higher. And one of the challenges of our industry is, and I don't have to tell you guys this because you guys are affected by it as well, but just to state it for the record, I think one of the biggest challenges of our industry is our customers expect our products, electronic products in general, to every year be half the size, half the cost, twice as fast, twice as long. It's almost diminishing returns. Even even Moore's law has been challenged.
For sure.
Like, are we at the end of Moore's law, right? I mean, is this possible? I remember back in the early PC days, Intel would have their 286, then their 386 processor, and their 486 processor, and their Pentium processor. And each time they released a new computer, the clock speed doubled. The original PC that my dad had, that I used to, practice coding on, was an IBM PC with 2 floppy drives, and its clock speed was 4.7 megahertz. And the next version, 4.7 megahertz. The next version that came out was 8, and then the next one was 16, and the next one was 32, 64, 128, 256, et cetera, 512. I'm going to run out of math skills if I keep doing that. And every generation, every year or so, a new computer would come out. It would be twice the speed. And then it started being 50% increase. Then it was 20% increase. Then it was, to your point, Jesper, earlier about iPhones. Every year we have a new iPhone, and every year they are a little bit faster and maybe an extra megapixel or 2 on the camera, but that's mostly a marketing move on their side. Yeah. I used to buy iPhones every year when they came out, and now I wait about 2 versions now until there's something a little bit more significant. Yeah. But the whole point in that rant was the evolution of boards are becoming is so fast, and boards are so complex, and for many the profit margin on these boards are minimal, and because let's face it, a lot of users of electronics feel like the electronic side of it is a commodity, which is offensive, but I can understand why they think that. Proper inspection, do it right the first time, is definitely driving our industry. I mean, now companies are making profits through optimization, and because they've cut all the cost out of everything, now they have to just be super efficient. And operational excellence.
Big initiative.
Right. That's probably what separates profit from nonprofit is how efficiently can we do things, and of course quality and inspection just falls right into that. So I'm carrying your flag, in the front of your parade, for inspection.
Appreciate that. Thank you.
I think that's very important.
Well, the other thing we didn't even talk about today, Mike, a whole nother topic, but when we talk about the future of inspection is the migration into the semiconductor assembly world,
right.
Both wafer level and packaging, and you mentioned Moore's Law, and so that's a horizon that we're on the cusp of right now, as well as people transitioning from the SMT world and migrating into this new space. So lots of opportunity there as well.
Those worlds are starting to merge a little bit.
They are.
I know with my involvement with SMTA, SMTA is getting involved on wafer level, ultra HDI things that traditionally were down the river in another village, and there is a good little bit of a merging, at least around the edges, which is great because
it starts
board
with
designers
system
need to know
applications.
Right. Board designers need to know how the real life problems of assemblers. We need to understand what board designers were thinking when they came up with this, way to build a board, and the wafer level people. We're all in the same village. We're all handing off, like a baton race. We're handing off the next baton, and all of a sudden the next baton weighs 900 pounds, and we can't carry it. We need to know that, ahead of time. So, it's good that we're starting to integrate. Joel, Scutchfield, Koh Young, Jesper Lykke, Viscom, thank you so much for being my guest today and for educating me and hopefully my audience on the attributes and technology behind inspection and the benefits and the advice in terms of best practices. I really appreciate your sage information.
Appreciate being fun. Definitely. We'll do it again anytime.
Absolutely.
Let's do it.
It's been
I
fun.
have a feeling we're not going to run out of subject matter in your world.
Yeah,
right?
you can tell, Mike, we have a lot we can talk about, right? All good. And we really like doing it, don't we, Jesper?
Absolutely.
Yeah. Well, when you love what you do, you never work a day in your life. So neither of you are working very hard. Yeah, it all comes naturally. All right, gentlemen, thank you so much. And if my audience would like to get a hold of Joel or Jesper, I'll have their contact information in the show notes. So if you're listening to this on your favorite podcast app, go to that podcast app and look at the show notes, and you'll find contact information for my guests there. If you're watching this on the YouTube channel, on the Reliability Matters YouTube channel, just look down where it says Show More and click on that, and you'll see the contact information there, as well as other information about this episode. So again, Joel and Jesper, thank you so much, and I'll look forward to our next conversation.
Thanks, Joel. Thanks, Mike. Appreciate it. Thanks,
you. Guys. Yep. Look forward to the opportunity, Mike. Always a pleasure.
Me too. Well, that's another episode. Thanks for listening to or watching the Reliability Matters podcast. Don't miss an episode. Subscribe to Reliability Matters on your favorite podcast app. If you're watching this podcast on the Reliability Matters YouTube channel, be sure to click the like, subscribe, and bell icons to be notified when new episodes are released. We release new episodes on the second and fourth Tuesday of every month. A special thanks to the Printed Circuit Engineering Association's PCB Chat at pcbchat.com and Ascendo Reliability at reliability.fm for syndicating this show. Thanks also for your questions and episode suggestions. Please keep them coming. I love to hear from you. Send comments or suggestions to Mike at mikeconrad.com. Just remember, that's Conrad spelled with a K. To learn more about the Reliability Matters podcast, please visit the Reliability Matters podcast website at reliabilitymatterspodcast.com. Once again, thanks for listening or watching. Until next time, stay safe, stay healthy, stay happy, and perhaps most importantly, keep doing it right. And I'll see you again in 2 weeks.
Thanks for listening to the Reliability Matters podcast. Join us on the second and fourth Tuesday of each month for new episodes of Reliability Matters.